many of the storms start North Pole and sweep down. What you're going to see here is images from a Marcy instrument that shows that a storm is starting. It's moving at about 60 kilometers an hour. And so that's the start of the storm. And if you look at the next view graph, you'll see that you have storms moving over the Martian surface. I've circled a series of storms to show you how you can follow it and how it spreads out and encompasses the entire region. You will see that in the center dot, there's the Opportunity rover. That's its location. And as you move from left to right and down, you will see that more and more of the features become obscured. Another view of this same thing shows you in June 22nd, you can see many of the traditional features on the surface of the planet. Olympus Mons, you can see the Tharsis Bulge, you can see the Hellas Basin. 3 weeks later, this is the image you see, and you virtually see none of the surface features. The only things you can really see are Olympus Mons and some of the other volcanoes that are peeking through the bulk of the atmosphere. So what does this mean? This is from a 300-kilometer altitude looking down at the planet. What does this mean for the rovers themselves? This is an image. These are a series of images that were taken by the Opportunity rover. Going from left to right, you can look at the top. There's tau. Tau is a measure of the transmission of light through the atmosphere. As tau increases, there's more dust in the atmosphere, and the ability to receive light on the solar rays decreases. So that you can see that this is just over this 5-week period, the tau increased from a little under 1 all the way up to 4.7. And you can see how dark it really gets there. At 4.7, you're getting about 2% of the normal light striking the solar array surface. What does that mean for the rover? You can see that the number of watt hours that are accumulated from the solar arrays drop as the tau goes up. And so you can see that we've got 765 watt hours, and it's steadily dropping. Now it got out to here about 3.5 weeks, and all of a sudden it seemed to be turning around. So there was a sigh of relief in the operations center that they had weathered the storm and they were going to move forward and start up a week or two. That did not happen. They got very surprised. As you see, the tau went up all the way to 4.7, and the actual maximum measured tau was 5.6. That meant that they were getting only 128 watt hours of energy. Normally, it takes them about 220 watt hours to survive. That allows them to have a 10-minute uplink, a 20-minute downlink, and allows them to at least do 10 minutes of science. Certainly, they would like to do that, more science in one sol, but that's the absolute minimum that they had. So the teams had to scramble dramatically to be able to account for this weather that was striking the surface. Just to give you a sense that this is not a singular event, this is a comparison of the Spirit and the Opportunity tau measurements against what they measured the Viking measurements to be during one of its dust storms back in 1976. And you can see they're very similar in the shape as it comes up and spikes and comes back down. This is an example of the actual accumulation of the dust. On the left, you're seeing tracks. You're looking at from the rear HAZ camera, and you're looking at the tracks that it made. And over the course of just 22 sols, that's about 3 weeks, those tracks are gone. If you look on the right, looking forward, you can see actually a wave of soil, loose soil, coming back towards the rover itself. So the soil is being modified in just the 3 weeks that we have been observing it here. This is the microscopic imager. This is on a clear day before the dust storm started. And this is what it looked like after 3 weeks. You can see that the clarity of the image is down because there's so much dust. And then you can see the coating on the imager itself. What did the teams do? They had to decrease their energy requirements. They did it incrementally. The first thing they did is reduce and eventually eliminated all science operations. They modified their heaters, and in some cases they had to modify the fault protection that was going on because they didn't want the heaters to come on. A fortuitous thing is that the atmosphere, although it got very dark, got warmer so that they didn't get as cold as they normally would get, and so they were able to reduce the amount of energy going into the heater power. Eventually the team had to adopt what we call the three-sol policy, where they uplinked one day, they sat idle for another day, and then downlinked the next day, just to survive during that period of time when the tow was the largest. The present status is that the tow is back down to 2.5, and both rovers are back to nominal operation. Nominal, I put in quotes because they do have arthritic conditions. Some of the wheels aren't working, and there are some other problems that they're having, but they are essentially back to full science operations. Spirit has mounted home plate. That's what you're seeing right here, this large rock, and is conducting science. An opportunity has entered into Victoria Crater. This is a picture of Duck Bay at Victoria Crater. And I circled an area here that represents the layer of rock of greatest interest in the scientist. This is the layer that they believe was at the surface when the crater was created. And they want to get back down to that surface so that they can look for signs of water that may have been there when the crater started. Above that layer is the ejecta blanket, and below is the bedrock. I'm going to show you a very quick video now from Opportunity as it approaches the crater. I hope I'm going to show it to you. No. I'm not going to show that, and I'm going to move on. Coming up. Here it is.
Maybe fortuitous. It's 8:45.
Yeah. Okay. This was created by Eric DeYoung and the Image Processing Lab at JPL. The data comes from the HiRISE instrument, was modified by the USGS and to a digital terrain map. So you're seeing right now an image of the 800-kilometer wide crater, and this is the view that Opportunity actually has of the entire Victoria Crater. This is the adjoining bay to the right. I think as you look at it, you'll recognize if you were steering the rover, you wouldn't want to come down this sandy path here, and you certainly don't want to get close to this rock ledge here. As I said, the crater is about 800 kilometers wide. It's about 90 kilometers deep. You can see the sand pattern that's being created in there as the prevailing winds are taking sand off the surface and bringing it down to the bottom. And this is Duck Bay, and that's where Opportunity, in fact, is This is an unreleased image. It's the first one taken by the NavCam by Opportunity inside Victoria Crater. So this is going to probably be released in the next week or so. You're the first ones to have seen it. I'm going to skip through Phoenix, although itself is an interesting story, and go to the MRO science. First, this is an image from the Charade radar. Roberto Seo, Professor Roberto Seo from the University of Rome, and Roger Phillips have created this image. This shows, this ground-penetrating radar shows the north polar cap of Mars. You can distinctly see the layers that are within the cap. This cap is kilometers deep. And you can also see the bedrock here, and you can see layering in the bedrock. So we are actually just starting to unfold the story that this ground-penetrating radar is able to provide for us. CRISM, which is produced by Scott Murchie in the Applied Physics Lab, is an imaging spectrometer, and it's making major findings. It's finding phyllosilicates in the exposed highlands. This is in the southern part of Mars. This is the older regions. They have no sense of water in this region, and yet these minerals are actually clays, and they're associated with the production within water. So now the question is, how did these clays get created and get located here when in fact there doesn't seem to be any major standing bodies of water? This is a dilemma that they're going out and working on right now. This is another image from CRISM. It shows very old rock. This rock is from 3.7 to 4 billion years old, and yet you're looking at composition that is very varied within that rock. The olivine is actually produced in water. So at some point during that 300 million year phase, in fact, there was water there that allowed olivine to be created. So what they're trying to do with CRISM is piece together the story of what happened during this 300 million year epoch. HiRISE is the major imager. It's finding some very interesting things. On the left, you can see there was a crater that was fresh. It was created while the mock camera has been up and operating for the last 10 years. It was not there, and then it was discovered, and you can see the HiRISE image, which is much higher resolution on the right. The interesting features here is that you're starting to look at the count of secondary craters. Counting craters is a fundamental method for determining the age of surfaces, but it's not clear that they haven't been overcounting craters, because one crater can produce ejecta that will create more. So this is the first time we're able to get some really accurate measurements of the ejecta created by a recent crater. There are some interesting gully troughs here that talk about the impermeable ground layer. This is a perspective. You may have seen this come out a year or two ago. Mike Malin showed that this white area here was not present, and then 3 years later it was found. It was thought to be caused by potentially water coming out. There looks to be certain features that this forking that goes on here suggested water at the time. HiRISE came along and made measurements along with CRISM, looking at the materials, and believe now this is the same that you can see up on top of the surface. And it does not appear to be formed that you can see up on top of the surface. And it does not appear to be formed by liquid right now. That being said, HiRISE has some other spectacular shots that do suggest some sort of water flow. It doesn't guarantee that it happened, but you're seeing beading, you're seeing islands being caused in these channels, and that really suggests that there was some sort of liquid flow in these craters. Geysers are very interesting things. There's a theory that was postulated by Hugh Kiefer that said if solar insolation penetrated the seasonal cap, it might heat up gaseous CO2 underneath to the point that it could explode into a geyser. There would be entrained in that explosion fine dust, and the prevailing wind would take the dust. And so you're seeing that kind of prevailing wind taking dust down here, if this theory is correct. Another example of geysers shown here. Again, these are the cold CO2 geysers that are created down at the South Pole, they believe. An interesting, this is the Russell Crater Dunes, is defrosting. In the wintertime it's completely covered and everything looks white, but as it as it warms up, areas are defrosting, and it's just a beautiful image. Another one of sand dunes and Candor Chasm. I'm skipping through to the Tharsis Mount. How are we doing on time?
You should quit.
Oh, okay. I will just tell you that we're finding some fantastic lava tubes that are larger than anything that we have ever seen here on Earth. And not only that, we have also seen Mars Pathfinder at the upper left-hand side, Spirit and Opportunity are shown there, and the two Vikings. So we are systematically trying to find the landers that we know of on the surface of the planet and viewing them. A couple of quick images of one from 300 kilometers and one close-up from the rover. And this is an unreleased photo of some of the hardware that helped Opportunity to get safely down on the planet. And with that, I'm going to leave just have a movie playing while I go ahead and answer any questions.
Okay. Is this working? No. Jim, maybe I'll. Can you turn on the wrong person?
Sure.
It's exciting to know about this fascinating program going on in Mars, and now I'm going to need your help. I'm Dick Klein. In a very short while, the people from the plenary event that comes after this thing are going to be coming in, and we do want to take questions. And I'm going to ask if somebody in the audio-visual areas can turn up the lights so that you all can see a little bit better. Can the lights be turned up, please? Now what we have is, you'll notice, two microphones, one over there and the other in this other aisle there. And what we'd like to do is we'd like to give an opportunity for as many questions as we possibly can now. And if somebody has a question, and I see that Bernard has already gotten over there, if you have a question, please walk up to one of those mics. If you want to walk up and stand in line, that would be fine. And then here's what I would like to ask you to do. Please clearly state your name, because this is being recorded, and your affiliation. Then ask your question in as briefly as you possibly can, so that we can get as many questions in this time period. So with that, let's begin with the questions. And Bernard, you're the first up there.
Thank you. I'm Bernard Frank from the European Space Agency.
No.
Do you get me?
No.
Bernard Frank.
Yes.
European Space Agency. I was very fascinated by your discovery of clays in the Southern Island. And
Bernard, there's so much of an echo, it's very hard for me to hear. If you come just down here, I'm happy to repeat the question.
Yeah, okay. Your discovery of clays in the Southern Islands, does it mean that you found clays where we didn't expect water?
Bernard, stop. We can't hear you. This is too bad. Either come up here or use the phone, Mike.
Excellent.
Good man.
Yeah. You found phyllosilicates, we call them clays, in Southern Islands, in places where we didn't expect water. So what does it mean, and at what time do you think these clays were formed?
They believe that the clays were formed early in the history of Mars, and there is a theory that they're working on that they were formed from the cratering process, where there may have been water available, there may be sufficient energy, minerals, and water that created them when the craters were first founded in the highlands themselves. That's the theory that they're working on.
Okay, thank you.
Ask for other questions.
Any other questions? Over here, yes.
Try the mic and ever come up here.
Hello, I'm Dr. Sarge from the Surrey Space Center. I'm a lecturer there. Well, this was a very fascinating breaking news.
It's so much of an echo, it's so hard for us to hear. Would you please come forward and...
Come use his mic. And if somebody else has another question, I suggest you come up here. This mics are just unusable.
My question is, one thing is relevant to the dust cleaning process, And let me start with that, because I'm just wondering, what's the technology behind this, vacuum cleaning or cleaning away the dust for micro rovers and, nanoscale rovers? Because does NASA has any particular technology, or are we developing this so that, we could look at more miniaturizing the rover technology? Because dust storms is a major problem for Mars, right?
Right.
So does NASA has any particular interest in developing, technology for cleaning up the dust so that we can go more into smaller scale rovers? Because otherwise, they'll get lost.
Let me just say that the rovers were initially designed to operate for only 90 sols. Those are Mars days. The reason that they're continuing to operate is because there is a cleaning process that naturally is happening on the planet, and that is the dust devils are coming along, the wind's coming along, and it's actually clearing off the solar rays and allowing them to actually remove the grime and the dust that gets up there and blocks those solar rays. And that's what's really enabled them to go forward and to operate. NASA did have a program of looking at alternative ways of cleaning off those solar rays, but that was a number of years ago, and I do not believe, I can't speak for all of NASA, but I don't believe that that's actively underway. I think that the next lander will operate for 90 days. It'll be a static lander, and there's no plans to try to clean that solar ray. And then after that, they will go to a thermopile, and they will not be using solar rays, so they will be actually not needing to have to clean the arrays. They have to keep the lenses clean, and there may be some techniques that, but I'm not aware of that.
Okay, thanks. And one more question. It's relevant to the locomotion, system for Spirit rover. Recently, it had this problem with one of its wheels got stuck. So how did that affect the mobility and the performance of the rover as a whole?
Actually, each one of the rovers has one problem with one of the wheels. In Spirit, the wheel is not driving, and so they actually have to go in reverse so they can actually they drag the wheel with them. In Opportunity, the wheel drives, but it doesn't turn, and that happens to be less of a concern for them. So they are struggling through that. Okay, you can't hear me. They are struggling through that, but they have managed to make all of the rovers work successfully.
So, are you interested in developing self-repairing rovers that has the capability of, solving small issues with the locomotion and things like that?
I can't answer that question.
Okay.
Yes.
All right. Thank you.
Any other questions?
No, Jim, that's
it.
Yeah.
Okay.
Oh. Thank you for that question. I would like to say that we should recognize that the activity that Jim has been talking about with Spirit and Opportunity were designed for a much, much shorter mission. They far exceeded their goals. The dust storm that he was relating to was something that was not at all in their design spec. They went into this sort of quiet mode and weathered the storm, figuratively, on that, and now it's come out the other side and it's working. So I think this is just